Hello, my name is Lucie Smetanova, and I work on this with Tatiana Polishuk, Anastasia Lemety, and Henrik Hardel. We are all from the Linköping University in Sweden, and Henrik also works at LFB. I would like to present the evaluation of the sequencing and merging procedures at 3 European airports using Opensky data. And I forgot to mention that we are cooperating or collaborating with the Eurocontrol Innovation Hub and LFV on this work. We are evaluating the various aspects of the arrival performance in the terminal maneuvering in the TMA for the different navigation procedures and different sequencing and merging techniques. We use a set of the performance metrics which are developed by the Eurocontrol PRU, which we adopted and enhanced, and in the TMA KPI project, which is supported by Swedish Transport Administration's Trafikverket, and in collaboration with LFV. We chose 3 different airports for this evaluation. We chose Dublin Airport for point merge procedures, Stockholm Arlanda for vectoring, and Vienna Airport for trombone procedures. We chose the most used runways of each of these airports in October 2019, and we evaluate the procedures inside the TMAs for Arlanda and Vienna. And for Dublin, we extended the TMA for 50 nautical miles circle around the runway because there is a lot of eastbound traffic which starts there. Its descent before it enters the TMA. For point merge procedures, we chose the Dublin Airport. As you can see in the picture, point merge has sequencing legs in the shape of arcs for path stretching. And we chose the main runway, which is 10R28L, which is used 95% of time. And the point merge is designed to work in high traffic loads. We have vectoring in Stockholm Arlanda Airport, which operates 3 runways, and the most used is barrel of parallel runways, where one of the runways is used for takeoffs and another one for landings. And Arlanda operates mix of closed and open stars, and we are using the runway which is on the picture here. For trombone, we chose Vienna Airport, which has 2 intersecting runways, which are used simultaneously to split the arrivals and takeoffs. Vienna has number of waypoints for path stretching and shortcuts. The datasets we use the states data from Opensky network, and we chose the 4 weeks of October 2019, which was the year with the highest numbers worldwide, and month with the highest number of arrivals at our 3 airports. We did a lot of data cleaning, and we used a set of methods. One of them is linear interpolation to fix the incorrect positioning, and Gaussian filter to smooth the altitudes. We removed trajectories which are too far from the TMA border, or which represents landings too far from the runway, or that are incomplete within the TMA, for example, go around. We also removed flights with call signs with only digits or only letters, or that have call signs shorter than 4 symbols, because it's usually the special purpose flights, and we would like to we wanted to consider only the commercial flights. We developed 3 different types of data sets. First is PM data sets, which is for point merge procedures in Dublin, and it contains only flights with adhere to point merge. And we chose trajectories which pass the SIVNA or COGAX waypoints, which are highlighted in red in the upper picture. The dataset contains 45% of flights. Next, we have the TB datasets, which is the trombone datasets for Vienna, and it contains only flights which go to the trombone procedure. And we chose trajectories which pass selected waypoints or pair of points, which are again shown as red dots in the picture. It contains total of 40% of all flights. Next, we did TT dataset for each of the airports, which has peak time periods, and it contains all flights with significant average time in TMA which have significant average time in TMA. For fine grade evaluation, we have small subsets, 1 hour subsets from these TT datasets for each airport, and we have 2 types of the fine grade evaluation subsets, which is busy hours and the most delayed hours. Busy hours are hours where there was significant number of flights and with the good weather conditions, and the most delayed hours are where there are hours with the highest average time in TMA. We use several performance metrics for horizontal flight efficiency. We use additional distance metric. For this, we clustered the trajectories in TMA by border points. You can see the different clusters in different colors in the pictures. And the additional distance is calculated as the difference between the ideal reference trajectory, which is marked in black in the pictures, and the real trajectory. We have time on flight levels, which is to evaluate the vertical flight efficiency. And it's the difference between the reference trajectory, which is made by the continuous descent profile, and between the real flight vertical profile. Also, we have additional fuel burn environmental efficiency, which is again the difference in fuel consumption of the ideal reference trajectory profile and the reference profile of the real flight. And we use Eurocontrol BADA for the fuel consumption calculations. Next, we have minimum time to final, which is one of the metrics of the sets developed by the Eurocontrol. And we overlay rectangular grid over the TMA. Each cell has 1 nautical mile of side, and it's the minimum time needed from any point in each cell of the grid to the final approach. We also have our new KPI, which is horizontal spread, and it's good to estimate the percentage of TMA area occupied by the flights and quantify the dispersion of the arrival flows. It is calculated as the ratio of the number of cells through which at least 1 aircraft have flown and the empty cells in TMA. We have spacing deviation, which is the difference between the respective minimum times to final of an aircraft pair. It is calculated by the formula shown on the slide, where the trailer is the aircraft which arrives later to the final point, and leader is the one which arrives first, and the S runway is time separation between those two. Also in the picture, you can see evolution lines of the spacing deviation in time for each of the aircraft pairs, and the black curves are the 90% confidence interval. We also have throughput metric, which is the number of aircraft with the same minimum time to final within a given time window. We use ISO minimum timelines from 600 to 30 seconds to final, with 30 seconds sampling rate over 5 minute periods. Lastly, we have metering effort, which is the difference between the throughput at the given time and the throughput at the one close to the final, and it quantifies the controller's effort for metering. Now we can move to the results section. We have results for the large scale analysis. And here we have the horizontal, vertical, and environmental efficiency. I would like to talk first about the first three boxes in each of the pictures, which represent the TT datasets. And we can see that Dublin is in pink, and Dublin shows higher median values for additional distance than Arlanda and Vienna. But Arlanda and Vienna has similar median values, but Vienna has higher dispersion. This disposition is similar in all of these three metrics. Now we can look at the last two boxes in each of these pictures. The second pink box is the point merge procedures, and the second blue box are the trombone procedures. And we can see that the performance of the airport is better when the flights adhere to point merge procedures. And for trombone, the median values raised, but the dispersion lowered. Here we can see the minimum time to final heat maps, and the horizontal spread is much larger for Vienna than for Dublin and Arlanda, where the value is around 60%, and such a large area of dispersion makes a larger area to control for the air traffic controllers. And the minimum time to final shows significantly higher values for Dublin. The results are in line with the results for additional distance. We also have this spacing deviation evolution lines for each of the airports, and we can see very big difference in the width of the 19% confidence interval. We call it the 19th quantile, and it's the width between the black curves in the pictures. And as we can see, the shape of each of these figures or evolution lines can indicate each of these procedures. Here we have the throughput and the metering effort. It shows when the metering is actually applied during the approaching to the runway. In Dublin, it's quite far away from runway. There is continuous descent in metering for Arlanda, and it's very close to runway in Vienna. Now we have the fine grade analysis. We have again these three vertical, horizontal, and environmental efficiency metrics for these. And we can see the busy and the delayed hours in here. And first, what we can notice is that the values or the numbers are significantly higher for these 1 hour scenarios than for the full month in TT datasets. We can also see that only in Arlanda, the additional distance metric has improved during the busy hours. And also we can see that performance is worse for the delayed hours, which results from longer paths in TMA. Which also the traffic intensities are handled better than delays. And we can see it especially in Vienna, vertical efficiency and additional distance in Dublin. Here we have some numbers for the fine grade analysis for the sequencing and metering metrics. And we can see that there is higher minimum time to final for the most delayed hours and higher horizontal spread for the busy hours. but Dublin has the lowest horizontal spread from these three, and that's because the flights are flying on the predefined paths, and they're clearly following the path. There is larger 19th quantile width for spacing deviation for Dublin and Vienna, but smaller for Arlanda. That can be caused by the fact that Dublin and Vienna use a lot of path stretchings, and Arlanda is not. And there are higher values for metering effort during the most delayed hours for Arlanda and Vienna, but lower for Dublin, which can mean that Dublin has predefined paths and it doesn't need so much air traffic controller sections. And in conclusions, we evaluated the arrival efficiency at 3 European airports, and we saw that the adherence to designed route procedures improved the efficiency at Dublin, but the results for Vienna are ambiguous. All of our airports perform better in high traffic scenarios than in delayed periods, and horizontal performance is improved in congested scenarios in Arlanda, and Arlanda seems to be better in delays than the point merge and trombone procedures. Also, no fair comparison can be done without considering the entry conditions to the terminal, and further studies would be needed to analyze that. Thank you, and I'm open for questions.
Okay, thank you very much, Lucie.